Section 12.5, Triple Integrals, Video 8. Between the previous video and this one, I did glance at the textbook to see why the author's approach was different from mine, and I realized what the author did is said, let's try approaching this from a bounded by the top, bounded by the bottom approach. Remember, we did left to right because both equations were y equals something. And then that approach crashed and burned, which is what I thought our approach was going to do because it was different than the author's initial approach. So the author was actually illustrating on page 724 what I was saying a moment ago, that sometimes you set something up from a certain perspective. In this case, we set it up from a left to right perspective. That seemed natural. And you push it until you either finish it or until it breaks. After the author sets up a failed attempt, then he continues to take the same approach that we're taking. So luckily my intuition was going in the correct direction. If you want to see an example of how approaching this problem from bounded on the bottom and bounded on the top crashes, I strongly recommend reading page 724, example 3. It takes until the beginning of the next page to crash and burn, and then they shift gears and do exactly what we're doing. So what are we doing? Well, we were evaluating this triple integral over the region defined as bound between this paraboloid and this plane. We managed to go ahead and set up a dy integral first because we pictured the region as being bounded on the left by the paraboloid and on the right by the plane, and it got us here. That's pretty messy looking. But one thing's been crossing my mind ever since we've gotten to this point. It actually popped in my mind at the beginning when I saw this. This reeks of polar coordinates. I know polar coordinates are all about x's and y's, but the truth is the names of variables are 100% arbitrary. In other words, there's no reason we can't talk about polar coordinates on the xz plane. We would just have to be careful in how we define them. Recall that in polar coordinates, to get to a point, this would be xz, not xy. To get to a point on the plane, instead of going over and up, we rotate and run. The angle that we rotate is usually called theta, and the distance we travel is usually called r. So if we were to set up polar coordinates in the the xz plane, instead of the xy plane, then our conversions would be x equals r cosine theta, like it was before, but z equals r sine theta. So let's take a polar coordinate approach because there's so many things that just scream it. Number one, this is a circle. The circle is really easy to define in terms of polar coordinates. The radius on this circle, or rather I should say the circle and everything inside of it. I should clarify that the region is not just the boundary, but all the points on the inside as well. So the radius of every point on here is between 0 and 2. Remember, it's a circle of radius 2 because 2 squared is 4. And our angle can rotate all the way between 0 and 1 complete revolution. I can get to any point on here by traveling the correct radius and then rotating the correct amount. So this is real easy to define in terms of polar coordinates, and this is loaded with x squared plus z squareds. If you recall in polar coordinates, x squared plus y squared equals r squared. Well, same thing here, except x squared plus z squared equals r squared. So we're going to trick this out into a polar integral. Just remember one thing. When you convert to polar integrals, the dA picks up an r to go with dr and d theta. So let's make this transition to polar coordinates. X squared plus z squared becomes r squared. So this becomes 4 times the square root of r squared, so it becomes 4r. Remember, we always assume the radius is positive. Minus x squared plus z squared becomes r squared, but r squared to the 3/2 power, you would multiply the exponents, the 2's would cancel, and when we get r cubed, this is suddenly becoming easy. But don't forget, in polar coordinates, the dA, this is what I call a thought cloud, becomes r dr d theta. So r dr d theta, we're going to integrate with respect to the radius first. It really doesn't matter. The radius goes from 0 to 2. The angle goes from 0 to 2 pi. Now this suddenly becomes a really easy back-to-back calculus 1 problem. Let's do the inner integral first and then import the results back into the outer integral. So the inner integral is the integral from 0 to 2. Let's go ahead and distribute the r to get 4r squared minus r to the 4th, dr. The antiderivative of 4r squared is 4/3 r cubed. The antiderivative of r to the 4th is 1/5 r to the 5th. And this is being evaluated from 0 to 2. If I substitute 2, 2 cubed is 8. 8 times 4 is 32, so we get 32/3 minus 2 to the 5th is 32. We get 32/5. That's the value from substituting 2. It should be pretty evident that substituting 0 gives us 0. So 0 gets subtracted from that. And if we get a common denominator and do the math, I believe we're going to get 64/15. Let me do that again real quick. 5 times 32 minus 3 times 32 is 2 times 32. 3 times, okay, that's correct. All right, so the value of the inner integral is constant. So we can resume with the double integral and import this result back in for the inner integral here. Integral 0 to 2 pi of 64/15 d theta. Finally, something easy. 64/15 theta is the antiderivative from 0 to 2 pi. Substituting 2 pi would give us 64 times 2 pi, which is 128 pi over 15. Substituting 0 would give us 0, so we would subtract 0 from that, and we're done. Booyah, that's exactly what's on page 725. So, just because we go from one section to another doesn't mean you can figure what we just talked about. In this case, polar coordinates snuck in, but honestly, if you do enough of these, I looked at this and thought, please do polar coordinates, because calculus on things like this is sometimes difficult and other times impossible. That's why polar coordinates are so sweet. They can take things that are impossible and make them so simple.